right, I guess it's time for our TAP colloquium. And we're very lucky to have Miki Nakajima visit us from University of Rochester, Rochester University, where she's in 3 departments. And I have to remember, it's Earth and Environmental Sciences is her primary department. And then she's also in Astronomy and Astrophysics and in lasers, laboratory for laser energetics. Okay, so you can ask her about her laser work later. Miki got her undergraduate degree at Tokyo Tech with Shigeru Ida, and got her, then spent a year at UC Santa Cruz, where I met her in 2008 as a visiting student with myself and Doug Lin. And then she was a PhD student, got a master's back at Tokyo Tech.
Yes,
it was Tokyo Tech with Shigeru Ida and Hidenori Genda, and then was at Caltech for a PhD with Dave Stevenson, where she made herself known for a lot of the theoretical work relating equations of state and planetary physics to the giant impact factor. And then was at Carnegie as a postgraduate fellow for 2 years. And then is now an assistant professor at University of Rochester, and is going to talk to us today about origin of moons in the solar system and beyond. And I wanted to say one of the hallmarks of Miki's work is really bringing a lot of geophysics and planetary physics into a really complicated set of phenomena that are really important for habitable planets throughout the universe. So Miki, take it away.
Thank you so much, Eric, for the great introduction. And I learned a speech from Eric, so you are the reason why I started all of this. So thank you for the great education. So today, I'll be discussing origin of moons in the solar system and beyond. So first, I'd like to 1 second. Copy moves. Should move. Okay, great, it worked. Great. First, I'd like to thank my collaborators who make this work possible, and also funding agencies. And I also want to thank my daughter, Hannah. She's about 4 months old. She's very cute, and she has been a great collaborator. She hasn't contributed to science part that much, but she gives me a lot of moral support. So I wanted to introduce her. Great. So I'll talk about 3 different topics. First, I'll discuss origin of the Earth and Moon, and then talk about implications for exomoons. Exomoons are moons around exoplanets. And then in the end, I will discuss ongoing work. So first, I'd like to ask a question. Why do we care about the moon? For me, this answer is very easy. So the origin of the moon is the same as the origin of the Earth. So the moon formed at the moon formation was the last step of the Earth's accretion. So that determined the initial condition of the Earth. And also, I hope many of you saw Artemis launch. I kind of fell asleep 15 minutes prior to the launch, but it's very exciting. And then we are going to learn a lot about the moon from ongoing and future missions. And why do we care about the moon? So the moon affects the ocean tide and the biological cycles, so it affects us so many ways. And also the moon affects the length of the day of the Earth, and also affects the stability of Earth and spin axis tilt. The spin axis tilt is called obliquity, as you can see. And because of the moon, now it's stabilized around 22 to 24 degrees or so. And so the moon may contribute to stable climate on Earth. And but also I should mention the stability of planetary spin axis tilt depends on many factors, such as the initial obliquity, mass ratio, and such. So it doesn't. So this means that we don't really have to have the moon to have a stable obliquity and a stable climate. But at least for the Earth, this seems to be a good condition to have. So let's look at the historical hypothesis of the lunar origin. So this is prior to the Apollo missions. And the first one is a so-called capture hypothesis. An asteroid float through the Earth and got captured gravitationally, or perhaps the moon and the Earth form simultaneously. Or maybe the Earth is spinning super fast, and a part of the Earth got stripped off and made the moon. So there are several hypotheses. And then we went to the moon through the Apollo missions, and we now have much better constraints regarding the origin of the moon. And we left seismic stations on the lunar surface, and we also brought back some lunar rocks. And we found that the moon has a very small iron core. The radius is around 30 kilometers. And also based on the analysis of lunar rock samples, we know that the moon is depleting volatiles, such as the potassium, rubidium, and sodium, and many other elements. And one surprising fact was that Earth and Moon have very similar isotopic ratios. So this has been confirmed in many isotopic systems, such as oxygen, silicon, tungsten, and many others. So this was quite surprising at the time, because naively we thought that each planetary object has its unique combination of isotopes. For example, Martian isotopes are quite different from terrestrial isotopes. So it was surprising that the Earth and Moon have very similar isotopic ratios. So this may indicate that the Earth and Moon share the same source materials, or building blocks. Then, people looked at the previous hypotheses, and none of them really actually worked to explain the observations. Then the so-called the giant impact hypothesis came in. So this is a standard version of the giant impact hypothesis. So according to this hypothesis, the moon formed by an impact between the Earth and the Mars-sized impactor around 4.5 billion years ago. Here is the proto-Earth hit by a Mars-sized impactor and from a disk around the Earth. And the disk had a very high temperature, therefore it was partially vaporized. There's some like a vapor, silicate rock vapor, and also magma flying around the Earth, and the moon accreted from the disk. So this is the standard version of the giant impact hypothesis. And it's a bit hard to see from a cartoon, so I'm going to show you some of our simulations. This is the impact simulation done by one of my graduate students, Scott Hall, and probably as everybody knows in this room. So we use the smooth particle hydrodynamic method, and in short it's called SPH. The color shows the temperature, and you see an impact between the impactor and also the proto-Earth. And you can see that the surface of the Earth is highly shock heated, and impactor comes back and it gets completely destroyed by the impact itself and tide. And you can see the disk formation around the Earth. So this model has been favored for many reasons. So one of the reasons is that it can explain why the moon has a small iron core. So during the simulation, you can see that the iron core, the impactor, falls onto the planet. So there is not much iron left in the disk, and the moon accreted from the disk. So you think that this model can explain why the moon has a very small iron core, and it can explain the Earth-Moon angular momentum. And it could explain the volatile depletion of the moon if water escaped during the impact or subsequent processes. But this model cannot easily explain the isotopic similarities between the Earth and the moon. So when you track these particles, most of these particles are coming from the impactor. And that means that the composition of the moon should be quite similar to the composition of the impactor. And it is natural to assume that the impactor's composition is different from those of the Earth. This model cannot easily explain why the Earth and Moon have very similar isotopic ratios, except impactor just happen to have the same isotopic ratio. But we kind of have to do that. So that has been a major challenge for the lunar hypothesis for the standard version of the lunar origin. And since then, there are many hypotheses have been proposed. So I'm describing some of the hypotheses, and one of them is the Hard-Earth model. So in this case, there was a collision between two Hard-Earth-sized objects. So this is originally proposed by Kenneth 2012, and this is a reproduction in our work. And the color shows the molecular entropy. So you can see that here's a collision of two huge objects colliding with each other. Some people argue that it looks like a galaxy merger, but it's a very energetic scenario. And another one is the so-called fast spinning Earth model. So in this case, the Earth was spinning super fast, and therefore it had an oblate shape like that, and got hit by a small fast impactor. And that created a disk around the around the Earth. So in these scenarios, this scenario might be able to explain why the Earth and the Moon have very similar isotopic ratios. In a hard-Earth model, everything is mixed together. Therefore, the composition of the Earth and the composition of the Moon or disk should be quite similar. And in a fast-spinning Earth model, the disk is pretty much made of the Earth mantle materials. Therefore, this model could explain why the Earth and Moon have very similar isotopic ratios. And there are more models. The Celestia model is an extension of the fast-spinning Earth model. So the impact included the high angular momentum, high energy impact, and that created a complete vapor disk around the Earth. And over time, the disk cools and small silicate droplets emerge, and this sink to the midplane, and these droplets can merge to a single moon. So in this scenario, the disk would have been vigorously convecting. So any pre-existing heterogeneity, pre-existing mixed region could be completely mixed. So this could also explain why the Earth and Moon have very similar ratios. Or maybe the Moon formed by multiple impacts instead of one single impact. So the small impact that hit the Earth, that creates a small moon. Then another impact that hits the Earth, and that creates another small moon, and they might end up merging to a single moon. So if each individual impact is energetic enough, it could also strip off some Earth mantle materials, and that could explain the isotopic similarities between the Earth and the Moon. And also a hidden run collision from Eric and Eric's group. So they could have been just like a standard kind of size impactor, but actually goes somewhere else and it comes back. And in this process, things get more mixed compared to a conventional impact model. So this could be beneficial to explain isotopic ratios. And or this could have been an immediate moon formation scenario. So meaning that the impact that hit the Earth, instead of creating a disk, just the impact that kind of become part of the moon. So this is one of the latest research, which is interesting. Okay, so we talked about a bunch of models so far, and I'll just describe some of the lunar hypotheses here. And as I mentioned, so the isotopic similarities between the Earth and Moon could be explained in the energetic models, and the more standard model might have a bit more challenge to explain due to the not very extensive mixing. And in our paper we published in 2015, we looked at another constraint, which is the Earth mantle heterogeneity. So based on some geochemical studies, Earth mantle developed chemical heterogeneity early on before the moon formation. And we still have the remnant of mantle heterogeneity today. So that means that even though the moon forming impact was such an energetic event, it didn't completely homogenize the Earth mantle. So we thought this could be used as a constraint for the origin of the moon. So based on our simulation, so we conducted smooth particle hydrodynamic simulations, and then we found that in less energetic scenario, such as standard model, the mantle remains unmixed. Therefore, the mantle can preserve the mantle heterogeneity, so which is consistent with the geochemical observation. And we also conduct simulations for the more energetic scenarios, and we found that these impacts are so energetic that the mantle gets completely mixed, which might not be consistent with the geochemical evidence. So that's the result we published in 2015. So since then it's been some years, and so there is one caveat to this story. So the caveat is that it's actually hard to know whether the heterogeneity developed before or after the moon forming impact. So this story is based on the hypothesis that it developed prior to the moon forming impact. But if it happened after the moon forming impact, it's actually hard to constrain the lunar origin based on the mantle heterogeneity. So I'm still a big fan of my paper, but I know there are some caveats. So okay, what can we do? So that's the kind of main part of this today's talk. So before going to dive into the moon, let's take a little bit step back and talk about the moon, the plane formation. So first, let's discuss the classical plane formation scenario. So here's the star, and here's the protoplanetary disk, and there are some small planetesimals flying around. And these planetesimals accrete to each other. The planetesimals grow to Mars-sized embryos or protoplanets, and the gas dissipates, and the orbits of protoplanets become unstable, and they collide with each other. So this is called the giant impact stage, and we think the moon formed during this giant impact stage. Then the planets form due to the giant impact. So this is a classical model, but this model has a major issue, as probably many of the audience know. So that's called the classical meter barrier problem. So let me describe what this is. So here's a star, here's a particle orbiting around the star. The r is the distance between the star and the particle, and the velocity of the particle is a vp here. And the vp is a Keplerian velocity. So as you can see here, g is the gravitational constant, m is the stellar mass, and again r is the distance. And the particle is orbiting around the star with the Keplerian velocity. And the gas velocity Vg is not that different, but there's a pressure gradient term, and which is negative. So this means that the particle velocity is larger than the gas velocity. And that means that a particle feels a gas drag, and then it loses angular momentum and falls towards the sun. And this fall time scale is actually quite short. It's about 80 years if the particle was located at 1 AU. And this is much shorter than the planet formation time scale, which would be millions of years, tens of millions of years. And so this gas drag effect is the worst when the particle size is about 1 meter. If it's much smaller, then it can just fly together with the gas happily. But and if it's much bigger, it can be separated from the gas. So the 1 meter is the kind of worst, dangerous. So that's why it's called the meter barrier problem. And but this problem has been already solved. So I have expert in the room, so but I will just explain in my way anyway. But so the process is called the streaming instability. And imagine particles flying in a gas drag, and under some circumstances, these particles can cluster together. And this is sometimes compared to a cyclist clustering together to minimize the gas drag. So these particles experience a smaller gas drag. And once particles reaches the certain surface density, it can collapse by gravity, and the gravitation collapse. This could create 100 kilometer sized planetesimals. So by doing that, you are able to skip the dangerous 1 meter barrier. So you can go from small particles to much larger ones. Therefore, the planet formation can still continue. So that's the idea of streaming instability. Okay, so this is a revised modern planet formation scenario. So the pebble accretion scenario, the small particles, pebbles become planetesimals by streaming instability, and the protoplanets grow by accreting planetesimals and small pebbles. And large impacts are still required to reach the final planetary masses. So this is a more modern version of a pebble accretion scenario. Okay, so this is just a quick review of planet formation. And let's go back to the moon. Okay, so another parameter we didn't discuss was the vapor mass fraction of the disk. So in this energetic scenario, the vapor mass fraction of the disk is around 28%, meaning that the 28% of the mass is in the vapor phase, and 80% of the mass is in the liquid phase. This is like a liquid-rich vapor-poor disk. And but you look at the more energetic scenarios, they create more vapor-rich disk. So in some scenarios, the disk could be completely vapor. But that might be okay. Perhaps over time, the disk cools by radiation and make a small droplets, and they might just agree to a moon. But here, we propose that this could be a problem. So perhaps the droplets in a moon-forming disk might experience the strong gas drag. It might be lost to the Earth, just like the particles in a protoplanetary disk experience a strong gas drag. So let me do a very, very simple analysis. So here is the radial velocity of a particle in a moon-forming disk, which is a VR. And here eta is a pressure gradient parameter, and Vk is the Keplerian velocity. Tau is the dimensionless stopping time, which depends on the particle radius. And yeah, so if the particle is very small, then the particle can move together with the gas, but it's much larger, it gets decoupled. So yeah, so the dimension is stopping time depends on the particle radius. And just plugging in some appropriate values, we have the radial pole time scale for the growing moonlets in the moon forming disk. So the worst is when the particle radius is about 2 kilometers. So in that case, it only takes 1 day for the particle to be removed from disk. It just has a very strong gas drag and falls to the Earth very quickly within 1 day. And it's a little bit larger, a little bit smaller or larger. The residence time is around 1 month, but not very long compared to the moon formation time scale, which could be tens of years or hundreds of years or so. And if you get to like 1,000 kilometers in radius, it might be okay, but almost the size of the moon. So the thing is that so these could be a problem for forming the moon. Yeah, so pretty much similar to the 1 meter barrier problem. And yes, and then this is the problem only for the models which create the initially vapor-rich disk. And this is not going to be a problem for forming a moon from a vapor poor disk, because you can just make the moon from the liquid part of the disk, and the gas drag effect is not very strong. So this is only a problem for a initially vapor-rich disk. Okay, so here is the problem. So growing moonlets likely to face the kilometer barrier problem, meaning that the kilometer size moonlets fall the Earth on a very short time scale and in a vapor-rich moon forming disk. Again, this is not a problem for a vapor-poor disk. And here's the question. So can streaming instability solve this problem by making much larger moonlets very quickly, just like a streaming instability solved the problem for protoplanetary disk? And we investigate whether streaming instability can help forming the moon from an initially vapor-rich disk. Okay, so we conducted hydrodynamic simulations using a code called Athena, and we conducted the 2D and 3D simulations. And here's just a rough sketch of a coordinate. So X is the direction from the Earth, and Z is parallel to the Earth's spin axis, and Y is perpendicular to X and Y plane. And the coordinate is orbiting together, orbiting the Keplerian speed. And here are some, here's a list of parameters, and we use some normalized pressure gradient in the disk. So this is determined by the impact simulation. And we also looked at the dimension and stopping time. So these numbers are corresponding to a particle radius of 2 meters to 20 kilometers. And the particle to gas, we also vary the particle to gas ratio. And we also use the normalized gravity only for the 3D calculation. So we conducted a bunch of 2D simulations, and we also conducted a few 3D simulations as well with the gravity. So here I'm showing 2 n-member scenarios. So this work is led by a former undergraduate student, Jeremy Atkins. And we are showing 2 n-member scenarios. And here is a parameter, and the x-axis is the x normalized by the scale height. And the vertical axis is normalized by also scale height and the component. And the color shows the particle density. And for the first one, we don't see any concentration. So in this case, streaming instability is not likely. But when we decrease the pressure gradient parameter, we start seeing a bit more, I guess, promising scenario where where you can see a particle concentration. So we did 50 2D simulations and narrow down what the parameter space are probable to that lead to streaming instability. So these are clumps. Okay, and actually to track the moon formation, streaming instability, we have to do a 3D simulation with gravity. So this is what we did. So this is a parameter we used. Again, the color shows the particle density, and then the horizontal axis is x normalized by scale height, and now we are looking at the y normalized by the scale height. So this is a very quick simulation. So make sure to keep your eyes open. So you can see that I can run it again. All the fun stuff happens in the first few seconds. 1 second. Okay. you can see the particles forming, they're forming moonlets due to streaming instability. So we are confident that at least in this parameter space, the moonlets can form by streaming instability. But here's some kind of caveat, I guess. So we ran a bunch of simulations and we found that the maximum moonlet size is about 50 kilometers in size, and which is actually not very big compared to the dangerous 2 kilometers. So these moonlets are still very small. It's not big enough and still falls onto the Earth very quickly within 2 weeks or so. And so we found that streaming instability can happen in the moon forming disk, which is exciting. But our conclusion is that it may not change the big picture. The streaming instability induced moonlets are not large enough to avoid a strong gas trap. And yes, but but how about the evolution? So we are kind of only looking at the initial condition and what happens if the disk cools. And so once disk cools enough, the gas drag becomes weak, and the disk can start forming moonlets. However, during the disk cooling phase, a significant portion of the disk mass could be lost, more than 80%. So here is a calculation. The x-axis shows the radial distance from the Earth, normalized by the Earth radius, and the y-axis shows the surface density of the disk, and the different lines with different time steps. So you can see that disk is a very simple calculation, but the disk viscosity evolves, and during the process, a significant mass could be lost. So the idea is that so after the disk cools, the significant mass will be lost. So as the disk has a small vapor mass fraction, you can start forming a moon, but by the time significant disk mass is lost, so you end up making just small moons instead of a large moon. So in the next slide, I'm going to show you the schematic, like a big picture view of what I'm trying to make. So let's start with the large impactor that creates a complete vapor disk. And over time, the disk cools and the small droplets form by small silicate droplets form due to the cooling. And these small droplets are well coupled with the gas. And so they are happy. But over time, the small droplets start accreting with each other. And once they reach 100 meters to 100 kilometers in size, they start experiencing a strong gas drag and just falls onto the Earth pretty quickly. And this continues to happen. And over time, as I mentioned, the disk cools and the disk mass decreases, and over time disk spreads. And by the time the disks are forming a moon, there's not much mass left in the disk. And so you might be able to make a moon, but not large. So if you start with the initially vapor-rich disk, you might end up making a very small moon instead of the large moon. So which might not be consistent with our moon. Okay, so our hypothesis is that we prefer not very energetic model. So these models may be more consistent with the mass of the moon. And so there are actually additional constraints. Fortunately, we don't have time to discuss in detail in today's talk, but I'll just briefly mention what they are. And so as I mentioned, so the moon is depleted in volatiles compared to the Earth, but we actually don't know the process very well. So we think that these volatiles escaped perhaps during the moon formation or after moon formation, but we don't really know yet. So we are still trying to figure out what the exact mechanism of the volatile loss. And due to the advancement of analytical capability of mass spec, now we are able to see very small isotopic differences between the Earth and moon. It's still they are still having a very similar isotopic ratios, but we can resolve very, very small differences. And this might argue that perhaps, especially from oxygen, maybe the moon may still have a small impactor component. So that might be why we have a very small difference between the Earth and moon. So so that's a hypothesis. And another big constraint is the angular momentum. So now moon is quite far away, but if you bring it back much closer to the Earth would have been spinning around 5 hours a day at formation. And as the moon moved outwards, slow down the spin. So assuming the angular momentum was conserved. So this is consistent with the standard hypothesis. But when you look at more energetic scenarios, actually the Earth would have been rotating about 2.5 hours a day at its formation, which is pretty fast. And some studies argue that still you could remove this angular momentum. Perhaps you could transfer the angular momentum from the Earth-Moon system to the Earth-Sun system. But it's a big debate. We don't know if that's really possible. And you also have to extract the exact right amount of angular momentum. So yeah, so there's a big debate going on. So yeah, so it's a very tough problem. And this is just a quick summary of what's going on. We have different constraints, isotopic similarities, and small isotopic differences, but accretion, mismatch, angular momentum, and lunar mass. So none of the model is perfect. But my personal preference is more like a standard model and such. But it kind of depends on who you ask. Eric, do you have any preference?
Wide open.
Yeah, so it's a very open field and also a very exciting area of investigation. Okay, so just summarize up until here. So we find that the initially vapor-rich moon forming disk is not capable of forming a large moon because growing kilometer-sized moonlets fall onto the Earth on a very short time scale, and streaming instability does not help forming the moon from an initially vapor-rich disk. And our model supports the moon formation model that produces a vapor-poor disk, such as the standard model. And one shown caveat is that we didn't solve the disk evolution, which is pretty complex. But now we have a postdoctoral scholar arrived in our group, so we're gonna investigate this issue and hopefully you have a better answer very soon. Okay, so now we are switching gears a little bit and talk about exomoons, so moons in extrasolar systems. Okay. So so far we talked about impact-induced moon and yes, that's called giant impact. And in the giant impact scenario, the maximum satellite to planet mass ratio is up to 0.1. So you can make actually quite large moon compared to the size of the planet. And perhaps the moon, Sharon, Martian moons could have formed by a giant impact. But this is not the only way to form moons. You can also make moons in a circumplanetary disk. So here's Jupiter and has a hydrogen, helium rich gas. I see the rocky dust flying around. Then you can create moons in a circumplanetary disk. But based on some previous studies, the maximum satellite to planet mass ratio could be 10 to the minus 4. This is a balance between the removing the loss of the materials and the incoming building blocks. And so yeah, this is kind of small. And you can also make a moon by a gravitational capture. And the maximum satellite to planet mass ratio is not very known, but at least in a solar system, it's kind of small, 10 to the minus 4. Regular satellites and Triton could have formed by this capture process. But the key aspect here I want to stress here is that a giant impact is an efficient mechanism to make a fractionally large moon compared to the size of the planet. And in a solar system, we see evidence of a giant impact. So for example, Maki's large core could have formed by an impact of stripped off Maki's mantle, and moon and also Martian moons could have formed by an impact, and Uranus's exomoon moon could have also formed by an impact. And even extrasolar systems, we do see some impact-induced dust and gas. They could have formed by an impact, and also the large planetary density variation in the same system may indicate an impact. For example, if you see a planet with a high density, it may have a large iron core. That may mean that there could have an impact that shift of the mantle of the planet. So we see some potential evidence of giant impacts in the extrasolar system as well. And so talking about, right before just talking about moon, I'll just briefly talk about exoplanet detection. And this is just transit method. And probably you have seen kind of thing already from 100 times, but let me just do it anyway. So the x-axis of the time and the y-axis of the brightness. So when this is a transit method, so when the planet goes across the star, you see a dip in the brightness. So this indicates the presence of an exoplanet. And so far, we haven't had any confirmed exomoon, but there are several candidates. And here's the 2022 paper from David Kipping's group. So x-axis shows the time, y-axis shows the relative intensity. And so they argue that this extra dip could be a presence of, with the evidence of presence of an exomoon, and which is very exciting, but also it's pretty close to the detection limit. So people are still arguing whether this is a real detection or not. So there will be more follow-up observations coming up. And yes. So here's a question. We see that giant impacts should be everywhere in the solar system and beyond, but we don't see many, we haven't seen any confirmed exomoon to date. So why is that? And there are several potential reasons. Technically, it's super challenging. And also the Kepler planets tend to be too close to their host stars. And therefore the gravity from the host star to the planet and their moons are very strong. And it's hard to have a stable moons around these planets for a long time. So that's a very good reason. And but we also have a bold hypothesis, which is that perhaps not all planets can make large moons. Perhaps only certain planets can form moons which are large compared to the planets. And so this is based on the previous part of today's talk. So let's assume that initially vapor-rich moon-forming disk cannot form a large moon. Whether a planet forms a large moon depends on the planetary mass and the composition. So if you have a large planet, the impact on this large planet tends to be more energetic. And yeah, you can think about hitting two large bodies like a car. We don't want to think about car crash, but if you have like a large two bodies crashing each other, and it will be very massive. But if you have like very tiny, small balls hitting each other, it's probably not too bad, right? So actually the same idea. And also it should also depend on the composition of the planet. So for example, if the planet is made of water ice, it's probably easier to form a vapor-rich disk compared to the rocky bodies, because it's easier to vaporize water ice compared to rocks. So that's what you are going to see in the next few slides. So we conducted SPH simulations to constrain the vapor mass fraction of moon-forming disks and planetary conditions that can form large moons. So here are model parameters, and two planetary conditions are considered. So what is a rocky planet? The mantle is made of a danite rock, and the core is made of iron. And for the icy planets, the mantle is made of water ice, and the core is made of a rock. And we also parameterize the total mass, and we also change the impact to total mass ratio, and we fix the impact velocity and the impact angle in this investigation. So here are two SPH simulations. So this is pretty much the same as the moon forming impact. So this is a collision between the rocky planets. And the color shows the mantle entropy, and the gray shows an iron. And then you can see that, yeah, again, the surface of the planet is truncated, and that creates a disk. And we also did the same simulation for the icy planets. And the mantle entropy is shown in blue and light sky blue. And you can see that the dynamics of these simulations are pretty similar, surprisingly. But thermodynamics are actually quite different. So here's a quick summary of our result. Now the color shows the vapor mass fraction of the moon-forming disk, and the x-axis shows the impact to total mass ratio, and the y-axis shows the total mass normalized by the Earth mass. And the right panel shows the impacts between rocky planets, and the left one shows the impact between icy planets. So first, let's look at the rocky planet version. So when you look at the large planetary total mass, you can see that when the planet is larger than 6 Earth masses, the impact creates a completely vapor disk. And this makes sense because the larger planet tend to create more energetic impact. Because the kinetic energy of the impact is scaled with the escape velocity of the planet, and that depends on the planetary mass and radius. And also, if impact is large, then they also tend to create more vapor-rich disk because the impact they bring more larger kinetic energy to the system. And right, and when we look at the 4 icy planets, so we see the similar trend. But the mass required for the complete vaporization is much smaller because, as I just described, it's easier to vaporize water ice than vaporizing rocks. The latent heat of water is much smaller than the latent heat of rock. So we find that rocky planets larger than 6 Earth masses and icy planets larger than 1 Earth masses produce complete vapor disks, which might not be best disks to form moons. So this is a quick summary plot. So we argue that whether an exoplanet can form a large exomoon depends on the mass and the composition. And the large rocky planets larger than 6 Earth masses or 1.6 Earth radii, and icy planets larger than 1 Earth masses or 1.3 Earth radii may now form large exomoons due to this effect. So you can kind of see this is a satellite forming region, and this is satellite formation is not possible region. And this is at least consistent with the Earth-Moon system and Pluto and Charon system. And we argue that perhaps in the previous exomoon searches, they may have looked at 2 large planets. We should focus on smaller planets. So we argue that we should look for exoplanets that are smaller than 1.6 Earth radii for future exomoon searches. And future observation with the James Webb Space Telescope may able to find exomoons. So I had some email exchange with David Kipping. So I'm very excited about the future exomoons. So it'll be, yeah, stay tuned. So that's our hypothesis. And yeah, I got a cool tweet from him that he was happy to have at least testable hypothesis. So yeah, very excited. Okay, so let's see. Hopefully in 5 minutes or some, I want to talk about some ongoing exciting work. Okay, so I'm gonna switch gears a little bit and talk about the dynamo. So for us, today's dynamo is produced in the liquid outer core. So liquid outer core made of iron, it's convecting, and that produces a magnetic field. And here, the presence of the solid inner core is actually quite important. When the solid inner core crystallizes, it releases latent heat and light elements at the base of the liquid outer core that facilitates core convection. But early on, 4 billion years ago or so, perhaps there was no iron, there is no solid inner core. So in that case, can we actually produce a magnetic field? But based on the paleomagnetic studies, there were actually evidence of a magnetic field back then. So how did the Earth produce a magnetic field? And there are several hypotheses. So one of them is called exolution model. So perhaps during the planet formation, the core could have acquired a bunch of light elements, and they could be precipitating, and that may have derived dynamo at the time. And another hypothesis is the dynamo generation in silicate. So based on some studies, there could have been the magma ocean, so made of magma, at the base of the mantle. So this is called the basal magma ocean, and they could have been enriched in iron. And if you squeeze rocks, iron-bearing rocks under high pressures, and it melts, this magma may be able to reach a very high electrical conductivities, and they may be able to produce a dynamo. So the squeezed magma can become metallic. So that's a hypothesis. And so we look at this basal magma ocean dynamo generation mechanism. And so what's the requirement for this model to work? So for this model to work, the electrical conductivity of iron-rich silicate magma needs to have a very high electrical conductivity. And but there is no actual measurement of the electrical conductivity so far. So our goal is to measure the electrical conductivity of iron-rich silicate, especially MgFeO. So at the University of Rochester, we have a laser lab where we shoot lasers, like super strong laser to the target. And some people work on fusions, and some people, like including myself, work on planetary science implications. And let's see. Right. So this is a target design of our first shock experiment done in February and June 2022. Here's our target design. So this is a plastic layer. And we shoot the laser to the first layer, have the quartz. This is the target of our interest. And that creates a shock wave through the material. And we look at the particle velocity and the pyrometry of the shock front. And that gives us material properties. So in specifically, we look at the reflectivity of the target sample. And using a Drude model, we can convert the reflectivity to electrical conductivity. So here are some pictures of the shot day. This is a very exciting day. So you spend 1 year to prepare for the day, and then you show up like for the best. So yeah, also we synthesized the target. So it also was a trial and error process, and then you see that it blows up in like nanosecond kind of stuff. So it's exciting and kind of scary. And here just a very preliminary result. But for example, this shows the velocity measurements and x-axis of the time, y-axis of the position. So we are kind of tracking the particle motion along the this axis. And so if there's any motion like this, you see a particle motion. So in this line, we are seeing a shock wave front reaching the plastic and the quartz interface. In this line, we see the shock front reaching the quartz and MgFeO. And we found very still preliminary. Preliminary results show that we reach around 400 gigapascal and 6,000 Kelvin pressure temperature range of MgFeO. But we did not melt the MgFeO, so we didn't really measure the reflectivity, unfortunately. So in our next shot, which is coming in March 2023, we are going to go with the much higher pressure, and then we should be able to measure the reflectivity. And using that, we can measure the electrical conductivity. So that's the goal, and it's very exciting. It's kind of nerve-wracking because you only have one shot a year. They just hope for the best, and let's hope for the best for the next one. And yeah, I'll just go very quickly, but also we look at the magnetic field geometry by running MHD simulations. So this work is led by Victor Lerm in our group. And so our question is, okay, you have a basal magma motion like geometry. So this shows a very small aspect ratio, and this is a large aspect ratio. Do they still produce a dipolar magnetic field, or what can we compare with the magnetic data to constrain whether the basal magma motion could have been a good mechanism for explaining the early dynamo. And let's see, I have just 2 slides, I think. And I'm also interested in collaborating with our scientists. So I collaborate with the Professor Dustin Trail, who is a geochemist. And we recently went to Sudbury Impact Basin, which is located in Canada. So here is the University of Rochester. So it was about a 7 hours drive. And we went there, collect some rocks, took some pictures, collect some rocks, put in my garden. So we have a nice rock garden made of shatter cone and impact breccias, which is really cool. So yeah, so the idea is that, so we are running impact simulation, and we also analyzing rock samples. So we are trying to understand how the Sudbury crater formed. And yes, and then once we figure out the model, we can apply the model to all the Earths, like yes, Hadean and Archean Earth, and to understand whether the crust at the time formed by impact or other processes such as subduction. And yeah, so we are combining numerical and geochemical and field work, and then we are trying to understand the plate, yeah, including plate tectonics on the Earth. So we are very excited. Okay, And I think that was it. So thank you very much.
You want to field your own questions?
Oh, sure.
Yeah.
Any questions?
So, in the context of the highly spinning Earth model that you were talking about,
Mhm.
you said a problem is to transport the angular momentum away from the Earth-Moon system.
Right.
I'm wondering, could you have two moons and then one of them just escaped and carried away the angular momentum?
Yes, I think it's possible, but let's see. Although some studies argue that I mean, you might end up making two moons, but they may tend to like merge to a single body. Yes, I think it's
Because
possible.
for the context of Mars, I've heard that one of the moons is coming closer and hence the angular momentum is decreasing and the other one's going farther, so it's carrying away the angular momentum in some sense. So
Yeah.
could something similar have happened to the Earth at that point?
Yeah, it could be. You could maybe perhaps lose. You might have to have like a close encounter from another body and capture the other moon. So that could be a cool way to move the angular. Oh, Eric.
Oh, yeah, go ahead, Henry.
Yeah, so first of all, I just comment, it's very interesting. You're studying the streaming instability in this context, and I guess the parameters are very different. And I
Right.
guess two of the main ones you showed are the pressure gradient, which is basically how hot things are, and then how many solids you have. And for the normal protoplanetary disk case, those are just sort of different numbers.
Right.
But here, I guess, because of the condensation as things cool, right, it seems like they're coupled.
Right.
Right, so is that how you, I don't know, you figured tracing it out during the condensation history?
I guess I would do so much simpler, I guess.
Yeah,
So we are assuming that, we are just parameterize the particle to gas ratio, and we use a standard setting for the in Athena. So yeah, I think we have a particle like Gaussian distribution and a gas distribution. So we haven't really taken into account the actual like physics of how the particles comes to the midplane and how that's the actual structure. So that, I think that could be something we should probably look into.
the other thing I'm curious about, if I can ask something quickly, is the so where is moon formation happening relative to the Roche radius? So like, for instance, you talk about something drifting into the Earth, well, it's not going to get all the way to the Earth, it's
Right.
going to get tidally disrupted.
Right.
And then if the moon is accreting right near there, maybe
Right.
it's not all lost.
Right. So I think first people are trying to create a moon right outside the Roche radius. And I think that's still the case, but you can also, let's see. So you could, let's see, so this could span inside the Roche radius to outside the Roche radius. And outside the Roche radius, materials can just accrete pretty quickly. From the inside Roche radius, of course, it's smushed. So, but the inside of the Roche radius, the disk could viscously evolve. There were some materials could be fed into the accreted body. So I think based on the Robin and Salmon and Rob Canop's work, you might start with 60% of the mass from the immediate after the moon forming impact. You have 60% mass outside the Roche radius, but 40% may come from materials which originate inside the Roche radius. So there could be some kind of interaction.
Yeah, I really like the table with all the models and the constraints and the checkboxes. So it seems like the isotopic composition is a particularly tricky one. Now I was wondering, how robust is that constraint in terms of, like, has anybody thought about maybe just the surface being isotopically similar, but not most of the mantle
Yes.
being similar?
Yes, good question. So looks like the moon seems to be heterogeneous. So some people argue that the surface composition of the surface could be different from the inside, and that has been discussed. But I guess it's a bit hard to constrain unless we can drill, I guess. Or perhaps maybe if you go to the South Pole 18 area, there was a huge crater. There could be some mantle material. So if we collect some samples, we might have better constraint of the radial or like the isotopic heterogeneity within the moon. But it's a difficult question. Yes.
Yeah, can I follow up on the same thing Samu was asking about, but from a different angle? It seems like the original model works pretty well, except for those isotopic constraints. Can you flip the question and ask how similar would the isotopes have to be for that model to work? And has anybody tried to do that? And we don't have very many data points. We've got Earth and Mars, really.
Right. Yes, there are a bunch of studies. So we have, let's see, the constraints are not just one isotope, but we have many isotopes.
Mhm.
And oxygen isotope is actually not too hard. Maybe if there's a extensive radial mixing inside the solar system, maybe you might end up making an impactor which have the same, pretty much similar isotopic ratios to those of the Earth. But I think a hard one is the tungsten isotope, so which changes during the impact phase. So once each body experiences any impact, that kind of reset the tungsten isotope. So people have been studying like, okay, well, what's the likelihood of the impact that happen to have the same tungsten isotopes? And typically the rate is like 1%, like a few percent or something. So it depends on whether you are glass half full, half empty kind of person. But I think like 1%, 2% might not be too bad, but still it is a challenging problem. So it's not possible. I still think that the most likely scenario could be the standard hypothesis. And then, even though the impact that happen to have the same tungsten isotope ratio is not very high, but it's not too bad.
I had a question.
Yes.
Could the Mars system, since Phobos and Deimos are so small, could that be a system that just ran out of pebbles? Everything dragged in and sort of
Yeah, it
like
could be, yeah.
reverse scenario?
Yeah, it could be. Although, let's see. Although I think that these tend to be more like solid rich because the impact is, but yeah, I think at least let's see. So I looked at the Robbins model published in 2018. But in their model, the disk was pretty much like solid. So the temperature was not very high. But if you end up making a very vapor-rich disk, that could be.
Yeah, it could be without water.
Yeah. Yes.
Any other questions? Yeah.
So
something.
for the surface density evolution, it looks like you had some kind of alpha this model.
Yes, kind of, yes.
But what kind of alpha values?
Let's see. So I used alpha value from previous work. 10, it's in a paper, but 10 to the -3 or 10 to the -4 or something. So there are some estimates based on like, okay, if there's a MHD in a disk, the alpha could be this value or not. So I just took member scenarios. Yeah, that's 10 to the -3, -4 kind of range. But yes, it depends on that factor. We don't really know for sure what the alpha factor is. Yes.
More generally, do the SPH models that you're running, because they do have a full equation of state, and some of those particles will be in the gas phase. So doesn't that moderately simulate the gas drag of the forming particles?
So it's so the SPH is not very good at simulating two phases at the same time. So when you have like a flying SPH particle, it can be a combination of gas and liquid. So it cannot actually look at that, separate the phases.
Right, because one particle is larger than the one. Yeah, it's just the resolution isn't fine enough to split everything into the appropriate ratio.
Yeah, if you have an infinite resolution, you
Yeah.
might be able to. But unfortunately, yeah, most of the time, one particle represents two phases, and we cannot really look at the gas drag.
Just have a second question on the what is you had like kind of a question mark in the box for the hit and run scenario and the isotopes. I'm informed what is the expectation for isotopes for the hit and run? Is that out of, I mean, that is out of our lab, but what is
Oh, well, it's like half, it's
like
detailed answer, but it's kind of in between, sort of splits the difference. It's hard to get, you can't get the same kind of mix. You can't get the same kind of homogeneity as you can get for like the Synestia model, but it's more energetic than the classical model, and so you have more mixing.
it's not just all earth debris getting kicked up and getting
No,
captured?
surprisingly, it's
Okay.
a fair amount of impact,
Yeah, so
but it's still, it's instead of 80% off, you're 50% off. And does that get you anywhere closer to the answer?
Sure.
Right, so it's better than that standard, but it's not perfect yet.
So oh yeah, go ahead,
Yeah.
Laura.
Sorry, last question. About the result related with your last paper with the exomoons.
Uh-huh.
Do you know if James Webb is going to focus in that type of planets right now? I mean, with the small sizes planet trying to found the first exomoons.
So that's I'm trying to push it, but yes. So I actually emailed with Professor David Kipping, and he said that yeah, he will try for JWST time.
Because I think it's very interesting. All the other groups that I know are focusing in large planets, and maybe they are not moons.
Right. Yeah, but it was like pretty difficult to look at smaller planets. So but at least this is a testable hypothesis. I hope they'll look at the smaller planets. It'll be very exciting.
All right, well, Miki's around tomorrow, has a few slots on her schedule. Email me if you want to meet with her. And otherwise, thank you very much.